Welcome, students. We're now going to be solving inequalities, meaning not equal statements. See that in there? And so we want to make sure that we are aware of kind of what they look like. We have seen them before. They are the lesser thans, the greater thans, the lesser than or equal tos, and the greater than or equal tos. Now, the key about solving linear equations or inequalities and applications is you always must graph. Okay, so if you see an inequality and I ask you to solve it, you can bet that there's going to be probably a graph to go along with it. All right, so let's look and see, because an inequality is not talking about one set point on the line or two set, or an ordered pair. It's talking about a region, or so it's going to have more than one correct answer. So understanding intervals of real numbers, solve linear inequalities, graph the solutions for linear inequalities, and solve applications by using linear inequalities. So let's look at some of those. This is about the number line. There is a one-to-one correspondence between the real number and the points on a line. That is, each point on a number line corresponds to one real number, and each real number corresponds to one point on a number line. In other words, if this is 3 right here on the number line, there is not going to be a 3 anywhere else on that number line. It's just going to be at that spot. There'll be a -3, but they are not the same number, are they, in the real number family? So we're good to go. So here we have some things, and it's very important that we pay attention to open interval and closed interval and half open. When you're graphing something on a number line and you want to say that it's x is greater than a and x is less than b, but notice that it's not equal to, you always use an open circle. When you're graphing it on a number line and it also includes the equal to part, it should be a colored in circle. So you can see that this is an open interval, open on both ends. This is a closed interval because it's closed on both ends, meaning that it also includes that point A and B. This includes everything up to A and everything up to B, but not A and B. And then this one here is half open. It's open down here, but it's closed up here. So it doesn't include A, but it goes to up to and includes B. And in the reverse here, it doesn't include B, but it goes down to and includes A. So we need to just remember, if you're asked if that's open or closed or half open, those are kind of the ideas of how those work. So here's also how you could write it symbolically. If here's the algebraic notation right here, x is greater than a, then you would have an open circle at a, and it goes on, it's greater than, so it's going to keep going on and on. Here we have an open interval where x is less than a, so open at a, and it goes on and on. And then we have the half open interval once again, where it starts at a, but it also includes a, so it's closed, and it goes on to infinity. And here it starts at a, it also includes a, but it goes to the left down to negative infinity. All right, so represent the following graph using algebraic notation and tell what kind of interval it is. Well, first of all, I'm going to just tell what kind of interval. This is open and open, so it's an open interval. And my x is everything in between there, so I'm going to put x, and it's between, but it doesn't include a -1, so it's greater than a -1, but it's less than 4. And so I can write it that way, and I've written it algebraically. The other thing that you can do is you know your endpoints, -1 and 4. You can put x in the middle, and then if x is in the middle, notice it's greater than, x is greater than a -1, but it's less than 4, and there's no equal to with it. Another way that you could kind of just help yourself figure that out by looking at a graph. And it's an open interval. Here one is, oh, I do have a closed part, but then that arrow tells me it goes to infinity. So that would tell me that it's a half open interval. And so x, in this case, it's going to equal it, but x is greater than or equal to 2. This one here, this looks like I've got a open and a close, so this is like a half open interval, isn't it? And we're going to graph that on a number line. So draw your number line. And then find the points in -3 and 0. And x is somewhere in between that, isn't it? Now notice at a -3, it doesn't include the -3. So I'm going to draw an open circle here. But at 0, it does include 0. So I'm going to draw a closed circle there. And then I just kind of shade in between here to show that it's in between there. And there they do the same thing. So rules for solving linear equations. Simplify each side of the inequality by applying the distributive property to remove any parentheses, just like we do with an equation, huh? And combine like terms. Add constants and variables to or subtract them from both sides of the inequality so that variables are on one side and constants on the other, just like we were doing with equations. But here's where it gets a little bit different. You're going to then go to the step divide. You're going to divide both sides by the coefficient or multiply by the reciprocal of the variables and reverse the sense of the inequality if the coefficient is negative. So if I multiply or divide by a negative with a coefficient, it flips the reciprocal or the coefficient, or it flips the inequality. So if I for once had a problem that had the inequality this way and I divided by a negative, that would then flip it over and we would then have it this way. So you got to remember to do that, okay? And then you can check. How you check is you're checking an area, and if that area is true, then you got it right. So here we go. Just a reminder, we did this a couple lessons ago, but X, you can read them from left to right or right from left. I like to always read from the variable to the number. And that's what they say here. Read the variable first. So X is greater than 4. Or X greater than 4, but always start with the variable, okay? In this case, start here. X is greater than a -2, and X is less than 5.1. All right, so here we're going to solve this. We're going to treat it as if it was just a regular equation. So the first thing I want to do, can I distribute? No. Can I collect like terms? No. So now I'm going to subtract 4 from each side. And then enter this way. And now I'm going to divide, and I'm dividing by a +5. And since it's a positive, I don't do anything to the inequality. It stays the same, and I get x is less than or equal to a -1. And if I were to graph that, I'm going to have a filled in circle, and my arrow is going to go less than a -1, so it's going to head to the left, and it's going to be an arrow saying that it's all the way to infinity. Okay? Now you can pick any number less than or equal to a -1. So any number in this area should make the statement true. So if they picked a -4, 5 times a -4 is a -20. -20 plus 4 is a -16. And -16 is less than a -1. That is a true statement. So yes, we've done it correctly. All right. On this case, there is no distribution to do. And it looks like I can just add or subtract my 1 from each side and add 2x to each side. So that's what we'll do. And I get 3x greater than 2. Now I'm going to be dividing by 3. It is a +3, so I do not have to touch the inequality, leave it be. And x is greater than 2/3. Notice it is not equal to, so when we graph it, it should be an open circle. And it goes all the way to infinity. And so any point along this number line that lies within this area, any point will make that statement true. But not 2/3 because it is not part of the solution. So I can have right up to 2/3, but not 2/3. Okay, here we're going to distribute first on this. Oh, this is called a compound inequality. It's in between. So I can do this 2 ways. I can write it as 2 separate problems. And then I can write the other one over here with the middle term part is the part that's shared. And I can work those 2 separate problems, or I can work them together, okay? And let's just go ahead and take a gander at what they do here. I do see if I work at 2 separate ones, whatever I do, it's like having now 2 balance scales, one here and one here. And if I do something to this side, I have to do it to this side and to this side. So we've got to keep our scales balanced. if we just work it as one problem. So they're going to work it as two different problems. Okay? Well, maybe. So they're going to rewrite the expression. Well, first of all, what did they do here? They first distribute that, and we have to do that first. And that's where we get this. Now, if we work from the center and we're working it as one problem, I need to add 2 to each side. So if I add 2 here, I've got to add 2 over here, and I have to add 2 over here. So a -1 plus 2 is going to be 1. These 2's will cancel out, making my 0, and 3 plus 2 will be 5. And so now I'm left with I'm left with 1 is less than a -2x, which is less than or equal to 5. Now, I want x to be by itself, and I want it to be positive, right? So I'm going to divide by a -2. And what happens to my inequalities when I divide by a negative? They should be flipped. And if I do it there, I have to divide by a -2 here and a -2 here. So let's watch and see what happens when I divide by -2. Notice all of a sudden, I'm going to divide by the -2. They're flipped, aren't they? Was going that way, now it's flipped. This one is also flipped, and I get a -1/2 greater than x, which is greater than or equal to a -5/2. Now on the number line, -1/2 and -5/2. I've got to find those two places. So I'm going to find a -5/2, and it was equal to, wasn't it? If we go back, let's look at that. X is greater than or equal to a -5/2, but it's less than a -1/2. So I find the two spots. I'm going to have a solid circle here at -5/2 and an open circle at -1/2. And then when I read it, X is greater than that. So I shade this way. But it has a stopping point because it says X has to be less than and not equal to that. Okay, so it's this region in here, including -5/2. And you can check it. If a -2, which is right here, makes it true, then we've got it correct. And is a -1 less than 2? And is 2 less than or equal to 3? And the answer is yes. So it is a true statement. Okay, so here we have a physics student. We could say it's a math student, has grades on their quizzes of 85, 98, 93, and 90 on 4 examinations. If he must average 90 or better to receive an A for the course, what score can he receive on the final exam and earn an A? Assuming that they're not weighted. Okay, your final exam will cost more or be worth more than the other exams. So here we go. Remember when we take and find the average of something, we add up the numbers and then we divide by the numbers that there are 1, 2, 3, 4. Well, in this case, we're going to take a fifth test. So we're going to add up these numbers, 85, 98, 93, and 90, and the fifth test, which we don't know, so let's call it X. And then we're going to add up those 5 scores and divide by 5. Now, our rule said back here, we must have an average 90 or better to receive an A for the course. So my average has to be greater than or equal to 90, doesn't it? Average has to be greater than or equal to 90 to get an A. So here we have basically a proportion, don't we? And so we're still working with an inequality, but we treat it right now as if it was almost like an equal. And we're going to times both sides by 5. Well, what they did is they added these up, right? These were like terms that they could add up. And then we multiplied both sides by 5, clear the denominator. And we get 366 plus x is greater than or equal to 450. Now, if we subtract 366 from each side, we're going to get x is greater than or equal to 84. So this students on the final must get a grade of 84 or better to get an A in the class. All right. Ellen is going to buy 30 stamps, some 23-cent stamps and some 41-cent stamps. If she has $8.34, what is the maximum number of 41-cent stamps she can buy? So we want to know the maximum number of 41-cent stamps. So we don't know the cost of the stamps, do we? Well, but we do. Yes, we do. We know they're 23 cents and 41 cents. We just don't know how much of each. She has $8.34. So what is the maximum number of 41-cent stamps she can buy? So let X equal the number of 41-cent stamps. Then 30 minus X equals the number of 23-cent stamps. Does that make sense? Let's think about it. If let's say I had 30 apples and they're red and green. And if I said there were 10 red, how many green would there be? And you'd say, well, 30 minus 10, right? And that would give you 20 green. Well, in this case over here, we have 30 stamps, and we don't know the cost of any of them. But if we say one is X, then it makes sense that 30 minus X is not the cost, but the number of other kind of stamps. So she can't spend more than $8.34. So she has to spend less than or equal to $8.34. So she is going to do 41-cent stamp oh my goodness, 41-cent stamps at X of them, plus 23-cent stamps at 30 minus X, that's the difference. And that should add up to being less than or at least equal to, can't go over it, can you? She doesn't have any extra money. And so we go ahead and solve that. We can clear the decimal if we'd like by timesing by 100. They don't though, they're just going to work it with the decimal. We're going to, they collected like terms to get the 18x. And then we're going to subtract 690 from each side. And we get 0.18x is less than 1.44. So x can be less than or equal to 8. We cannot buy any more than 8 41-cent stamps. If we do, then we're going to spend too much money. So x has to be less than or equal to 8. Now, what did it ask? Let's go back and look at that really quick. It asked us, what is the maximum number of 41-cent stamps? So we have finished the problem by just that. X is the max, 8 is the maximum number of 41-cent stamps that we can buy. That would mean we were probably, if we bought 8 41-cent stamps, we're going to have 22 of the other stamps, aren't we? Because 30 minus 8 is 22. So we're going to solve these inequalities and we're going to graph them. Let's just click on, okay. Take a moment, pause the video, and then you're going to go ahead and check your solution with me. All right, let's begin this first one. So on number 1, I'm going to subtract 7 from each side. So x is less than a negative 4. If I wanted to graph that, here's my number line. It's not equal to a negative 4, so I'm going to just put negative 4 here. And I'm going to draw a big open circle and an arrow this way, trying to making it with my arrow here showing that it goes to infinity. Okay. Number 2, I think I will clear that fraction by timesing everything by 6. And if I do that, I end up with 6 times x over 2 plus 6 times 1 greater than or equal to 6 times x over 3. These will reduce, giving me 3x plus 6 is greater than or equal to, these reduce to 2x. I'm going to subtract 6 from each side. And then I'm going to subtract 2x from each side. And I get x is greater than or equal to a negative 6. So here's my number line for that. I'm going to find the point negative 6. I've got an equal to, so I'm also going to make it solid. So it's part closed. And x is greater than, meaning it goes to the right of it. And I'll make my arrow telling you that it goes on to infinity, like so. And now number 3, our last one. This is a compound inequality. I am trying to get x out by itself. Let's look at the middle. What do I need to do? I need to subtract 1. If I do it here, I need to do it over here and over here. That leaves me with a negative 6 less than or equal to 2x, which is less than 8. And now I'm going to divide by 2. It's a positive number, so I don't worry about flipping my inequalities. They'll stay the same. Negative 3 is less than or equal to x, which is less than 4. Draw my number line. I'll just use this here. This will be the -3. This will be the 4. It is solid here. It is open at the 4. And I just shade in between. I give it a nice healthy yellow. It's all the stuff in between there, including the -3, but not the 4. And that is the end of this problem and this homework. Hopefully your homework goes well for you in derivative. Good luck and have a good day.